In this lesson, we're talking about what is friction, what causes it, friction and Newton's laws, static and kinetic friction, coefficients of friction, and the applications of friction. Friction. Think about it. What causes friction? What affects the amount of friction between two objects? And describe how your life would be different if friction didn't exist. So what I'd like you to do is I'd like you to first pause the video and answer these 3 questions. And then when you're done that, I want you to watch number 1 and explain why they couldn't separate the books. So very basically, friction is caused by the resistance of one object sliding over another object. So as object A slides over object B, there's going to be some resistance. And that resistance is known as friction. What affects the amount of friction between objects? Well, it depends on their texture. So if you have objects that are really bumpy, like this, like say you're trying to rub something against carpet versus hardwood, you're going to get more friction than if it's smooth, as I said, like hardwood. Secondly, if you have an object that's really heavy, mass is also going to affect it. So mass, and we're going to talk shape. And how your life would be different without friction. Well, a lot of things would be different. As a very simple example, you're able to walk because as your feet touch the ground and push against the ground is going to push back on your feet, and that push is going to be through friction. Think about walking on concrete versus walking on ice. A lot easier to walk on the concrete than what is on the ice because there's a lot more friction between your shoes and the concrete than there is between your shoes and the ice. Now, why couldn't they separate the books? Well, if you have one piece of paper and another piece of paper, they're relatively easy to pull apart from each other. But if instead of one, you have many, many pieces of paper, now what you're doing is you're magnifying the friction. You're getting friction between these 2 pieces, these two, etc. for the entire time. Not only that, but you're also increasing the mass because the mass is getting bigger the more pieces of paper that we are adding to it. So our mass gets bigger and the amount of friction touch points gets larger. So as we increase those touch points and that mass, it makes it really hard to pull the books apart. Friction. The analysis of friction is very important to practical situations since friction is present everywhere. Friction is a good and bad thing. It's good when our tires meet the pavement, and it's bad when reducing efficiency and or producing heat, and when we're slipping on ice. Friction. Friction acts in the opposite direction of motion. It's always going to oppose motion. So if I'm going to the right, then friction is going to go to the left. If I'm going to the left, then friction is going to go to the right. It's always going to try to stop our motion. And it's caused by the electrical forces between 2 substances. So not only does friction oppose motion, but it really opposes the net force acting on an object. So if you have a force of this way of 2 newtons, and you have a force going the other way of 1 newton, then you would get motion as a result, right? So friction is going to come along and it's going to prevent that motion. It's going to have friction to the left. Now there's 3 main types of friction: kinetic friction, static friction, and then air resistance. Air resistance is simply drag friction or fluid friction. So parachutes greatly increase air resistance and therefore slow skydivers very quickly. Friction and Newton's laws. One of the most important equations when we're talking about Newton's laws is F equals mass times acceleration. And not just any F, but the sum of the F's. So the sum of the forces equals mass times acceleration. We can rearrange and we can say that acceleration is therefore going to equal to sum of the forces divided by the mass. And since friction is a force, it's going to be accounted for in our sum of the forces. And it's going to apply when F net is 0, as in when there's an equal and balanced force, and when F net is not 0, in which case F net is going to equal to ma. Types of friction: static and kinetic. Static friction prevents a stationary object from starting to move. Kinetic friction acts against an object that's already moving. The magnitude of friction depends on the surfaces in contact with each other, i.e. a shoe and floor, and the weight of the object due to its mass. So this goes back to what I was talking about before. So let's just say you have your shoe and it's on a hardwood floor. Now the hardwood floor is very smooth, but if we zoom in on both, what we're going to end up seeing is the shoe is going to look like this kind of on the bottom, and the hardwood floor is going to look something like this. Still pretty smooth, but all these ridges are going to get in the way of each other. Now if we talk about the same shoe on carpet, at a far distance it looks pretty smooth, but when we zoom in, again that shoe is going to look very similar, but the carpet is going to be much more undulating, something like that. And as a result, all these ridges are going to get in the way of each other. And when those ridges rub against each other, that's going to cause more friction. So it's going to be more friction and less friction due to these ridges bumping into each other less and more. Static friction. The magnitude of the force needed to start a stationary object moving is the maximum static friction force. So what that means is that if we have an object on a flat table surface, and I'm pulling it this way, well, this static friction force is going to act in opposition to motion. Now there is a maximum to that static friction force, and at that max, any additional force will cause it to move. So if I make my applied force just a tiny bit bigger, and I just exceed it, so I get a small amount of motion, that's the force that just exceeds the maximum static friction. So if we go back to the part where they're equal to each other, and we say that's force applied, in this case we would say that force applied equals the force maximum static. So this fan example here is not moving. So which way is the static friction acting in this picture? Well, it's acting up the hill. So it's opposing motion. Motion wants to go down the hill, so static friction is acting up the hill. Kinetic friction acts on an object that's in motion. The magnitude of the force trying to slow an object's motion is the kinetic friction force. So as you're going down the slide, that's kinetic friction. As a train is moving, that's kinetic friction. If there's motion, it's kinetic friction. Coefficients of friction. The coefficient of friction is the ratio of the magnitude of the force of friction between two surfaces to the normal force between those surfaces. For μs, we're going to be talking about Fs and Fn, and for μk, we're going to be talking about Fk and Fn. This symbol here is called mu, and it's going to represent that coefficient of friction. Now we can rearrange these equations and solve for Fk and Fs, so the force of static friction and the force of kinetic friction, by taking the Fn, which we know is mg, unless we're on a ramp, in which case we'll have to change it slightly, and μk, which we are given, or we can determine by calculations. And then the same thing for Fs. Now determining the μs and μk for a given substance is done through experimentation, so you can look it up in a book, or you can figure it out through an experiment. So a few examples: rubber on dry concrete would be 1.1 for μs and 1.0 for μk. Dry steel on dry steel, 0.6, 0.4 respectively, and then you can see greasy steel is going to be 0.12 and 0.05. So you can see by putting grease between the steel, it reduces the amount of friction between those substances, because this mu value is determined based on the two substances involved. So if you have rubber and dry concrete, it's going to be different from rubber and wet concrete. Now the other thing you'll notice is that the μs is always going to be bigger than the μk. That means as soon as you get something going from rest, it's going to accelerate relatively quickly once you get it going, because you're going to jump from the μs to the μk once it starts its motion. Friction application. So all you're going to do is pause the video and describe how both of these strategies will improve driving safety in the winter. So the first one with the tire and the chains. So traction results from the points of contact between the vehicle and the road surface. Rubber tires produce traction through friction when the rubber makes contact with the hard paved surfaces. When snow or ice cover the roadway, tires are prevented from making contact with the pavement, and contact between the rubber and ice doesn't produce nearly as much friction. The μk between rubber and ice is less than the μk between rubber and asphalt. The chains, therefore, dig into the snow and ice, increasing contact and friction. They're going to kind of carve a pathway for the rubber to actually make contact with the asphalt if possible. This increased friction is going to increase traction and vehicle control. Additionally, the chains will dig into the snow and actually create traction by pushing against the snow and the ice that they've dug into. So before we move on to the next one, I want you to again pause the video and answer these two questions. Number one, what kind of tires provide the greatest amount of friction? And what kind of tires do race cars use? And why do you think this is? We're going to assume it's going to be dry conditions. Now, what kind of tires produce the greatest amount of friction? Well, that's going to be our flat, bald tires, like this. Now, most of the tires you see look something like this, with these little creases in them, and those are very important. So what they do is that they allow water to pass through these areas without getting in the way of the tire on the road. If the tire didn't have any of those, it would look like the one on the left, where the water is going to be between the rubber and the asphalt, which is going to reduce our friction. So we don't want that. We want as much tire touching the road as possible. And with these little grooves, most of the tire is still able to make contact with the road, and that's good. Now the question, however, was what kind of tires provide the greatest amount of friction in dry conditions? And that would be this guy on the left. Now, why does this produce the most amount of friction? Because it's the most contact. So you get the most contact points when the tire doesn't have those grooves than when it does, and that makes sense because the grooves don't make contact with the road. It's the actual tire itself that makes contact with the road, produces the friction, and propels it forward. What kind of tires do race cars use? Again, that depends on conditions, but we talked about a dry condition, in which case they'd use the tire that produces the most amount of friction, because that's going to propel the car forward the fastest. Now, our second example was with these sandbags in the back. So what this will do is that's going to increase the mass of the entire vehicle. The increase in mass is going to create an increase in Fn. An increase in Fn increases Fk using this formula here, because if we increase our Fn on the right-hand side, we have to increase Fk on the left-hand side. Friction application. A couple more. So how do each of the following reduce friction, and what's the result? So on the left you see a hovercraft, which has powerful fans that lift the boat partially out of the water. And then the other thing you have is on the right-hand side, and it's these joints in your knees, which are these fluid cartilage sacs that allow the bones to move. So again, pause the video and answer how each of these help reduce friction, and what the result is. So for the hovercraft decreases the boat's contact with the water. This results in faster rides with less wear and tear on the boat due to less resistance. So since the boat isn't plowing through the water as much, there's less resistance on the boat, it can go faster. The cartilage and fluid in your joints prevents the bones from rubbing against each other. The mu for bone on bone is going to be much bigger than the mu of bone on cartilage. So since the mu of bone on cartilage is less friction results in better, easier motion with less wear and tear on your bones. Check your understanding. A box of fish of mass 18 kilograms rests on the floor of a parked delivery truck. The coefficient of friction between the crate and the floor is 0.50 for μs and 0.41 for μk. The local value of gravitational acceleration is 9.8 meters per second squared down. What is the force of friction and acceleration if A, a horizontal force of 75 newtons east is applied to the crate, and B, if a horizontal force of 95 newtons east is applied? So I'll let you pause the video and answer these two questions. So the first thing we're going to do is we're going to draw our free body diagram. So there's our crate. It's 18 kilograms, and that crate rests on the ground here. Now we're told that the coefficient of friction between the crate and the floor is 0.45 from US and 0.41 from UK. And we're going to need that information to figure out if our object is moving, and if it does start to move, how quickly does it start to move. So for A, we're going to have a horizontal force of 75 newtons east. And we're going to say that east is that way, and it's positive. So what we need to figure out is what is going to be the force of friction on the crate. So for A, first we're going to figure out mu s, and we're going to see if it's actually going to start going. We know that mu s is going to equal to Fs divided by Fn. We're going to rearrange. We're going to say Fs is going to equal to mu s times Fn. Mu s, we're told, is 0.45. Fn is going to be m times g, which is going to be 18 times 9.8, and that's going to equal to 79.38 newtons to the left. Since Fs is bigger than the force applied, there's no motion. So that's the answer to A. There's no motion. For B, it says if a horizontal force of 95 newtons is applied. Well, we know that 95 is going to be bigger than the force of static friction, so it is going to move. So when it starts to move, we need to figure out how quickly it's going to move. So we're going to use our equation. F is going to equal to ma, and we're going to say sum of the forces. Acceleration is going to equal to sum of the forces divided by mass, and the sum of the forces is going to equal the force east, which is 95, minus the force of friction, which we'll figure out, divided by the mass, which is 18. So we need to figure out the force of friction. The force of kinetic friction is going to equal to mu k times Fn. Mu k, we're told, is 0.41. Fn, same thing, it's going to be mass, which is 18 times 9.8, and that's going to give us a force of kinetic friction of 72.324 newtons. So the sum of our forces on the right-hand side is going to be 95 minus 72.324 divided by 18, and that equals to 1.26 meters per second squared east. Now we need to have 3 stages in our answer, and that's what we have. So that's our final answer right there. Check your understanding. In the starting area of a 4-person bobsled race, the 4 athletes with a combined mass, including outfits, of 295 kilograms exert a minimum horizontal force of 41 newtons forward total to get the 315 kilogram sled to begin moving. After the sled has traveled for almost 15 meters, all 4 people jump into the sled, and the sled experiences a kinetic friction of magnitude 66 newtons. Determine the coefficient of static and kinetic friction. So I'd like you to pause the video and answer these 2 questions. So for A, we need to find the coefficient of static friction. So we're going to say mu s is going to equal to Fs max divided by Fn. Fs max is going to be just before it gets going. So what we're going to use is this 41 newtons. That is the force needed to just get it moving. And we can assume that just before 41, that's going to be the maximum static friction, because at that point it wasn't moving. So we're going to use 41. So we're going to say 41 divided by Fn. Now for Fn, we need to have the mass, and it's going to be the bobsled times the acceleration due to gravity. The bobsled is the thing we're trying to get moving. So we're told the mass is 315, and the acceleration due to gravity is 9.8. So we're going to have 41 divided by 315 times 9.8. And that gives us an answer of 0.0133 for our mu value. For B, we're looking for mu k. Mu k is going to equal to Fk divided by Fn. We're told that the kinetic friction is 66 newtons. So 66 divided by the total mass times gravity, because then the people are jumping into the sled at this point. So it's going to be the mass, which is going to be 295 plus 315 times 9.8. And that equals to 0.00949. And that's our kinetic friction. Check your understanding. 2 people are pushing horizontally on a crate of mass 25 kilograms. 1 person is pushing from the right with a force of 50 newtons, 1 person is pushing from the left with a force of 80 newtons. The coefficient of friction is 0.05. Find the acceleration of the crate. So I'd like you to pause the video and answer this question. So we're going to draw a free body diagram. The mass is 25 kilograms, and we're told that 1 person is pushing from the right. That means they're pushing left, 50 newtons. And 1 person is pushing from the left. That means they're pushing to the right of 80 newtons. The coefficient of friction is equal to 0.05. Find the acceleration of the crate. Now, these aren't the only forces acting on the crate, however. We also have the force of friction. Now, we know that it's going to go to the right. We're going to say right is positive. Since we know it's going to the right, we know friction is going to act to the left because it's going to oppose motion. That's going to be Fk. Now, what is Fk going to equal to? We're going to say that Fk is going to equal to mu k times Fn. Mu k, we're told, is 0.05. Fn is going to be the mass, which is 25 times 9.8. So 0.05 times 25 times 9.8 is going to equal to 12.25 newtons. So we're also going to add 12.25 newtons going that way. So now to find the acceleration, remember we say that F is going to equal to ma. That's our equation. We're going to rearrange. We're going to say that A is going to equal to the sum of the forces divided by the mass. The sum of the forces is going to equal to 80 minus 50 minus 12.25. And we divide that by the mass, which is 25. And that equals to 0.71 meters per second squared to the right. Check your understanding. A musician applies a horizontal force of 17 newtons west to an instrument case of mass 5.1 kilograms. The case slides across the table with an acceleration of 0.39 meters per second squared west. What is the coefficient of kinetic friction between the case and the table? So I'd like you to pause the video and answer this question. So we're going to draw our free body diagram. A musician is going to apply it to the west. We're going to say that that way is west, and that is positive. And we know it's going to have a force of 17 newtons that way. The case is 5.1 kilograms, and it's going to slide across the table with an acceleration of 0.39 meters per second squared that way, west. What is the coefficient of kinetic friction between the case and the table? So we're going to have Fk equal to mu k times Fn. We're solving for mu k, so mu k is equal to Fk divided by Fn. So Fk we need to figure out. Fn we know is going to be the mass, which is going to be 5.1 times 9.8. So now Fk is a little bit more tricky. Fk we're going to have to figure out over there. We're going to use the acceleration to figure that out. We know that the sum of the forces is going to equal to the mass times the acceleration. The sum of the forces is going to equal to this 17 newtons to the left minus the Fk to the right equals 5.1 times 0.39. Now we can isolate Fk. We're going to say that 17 minus 5.1 times 0.39 equals Fk. Fk equals to 15.011 newtons. Now we're going to put that number up in here, and we have 15.011 and divide it by 5.1 times 9.8. You get a mu k value of 0.30, and that's our final answer. Check your understanding. A 0.17 kilogram hockey puck sliding on an outdoor rink has a velocity of 19 meters per second forward when it suddenly hits a rough patch of ice that is 5.1 meters across. Assume that the coefficient of kinetic friction between the puck and the rough ice is 0.47. A. Draw a free body diagram of the puck moving on the rough ice. So we're just going to go ahead and answer that question right away. So our free body diagram is going to be 0.17 kilograms, and we know the mu k value is going to be 0.47. We're going to assume that the motion is this way, and that is positive, so we're going to say that the Fk is working that way. We're also going to have to draw in the Fn and the Fg. The Fg is going to equal to mass times gravity, which is 0.17 times 9.8, which is equal to 1.666, and that's also going to equal the Fn, 1.666. The Fk is going to equal to mu k times Fn. Mu k is 0.47. Fn we just figured out was 1.666, and that gives us an Fk value of 0.783 newtons acting to the left. Now B says, calculate the kinetic friction acting on the puck. Well, we just did that on the previous question. So the kinetic friction is going to be this, 0.783 newtons. So we're just going to say Fk is equal to 0.783 newtons. And we said motion was to the right, so we're going to say it's to the left. Now we only need 2 sig digs in our answer, so our final answer, our Fk, is going to equal to 0.78 newtons to the left. C asks, what determined the puck's average acceleration while on the rough ice? So I'd like you to pause the video and find A. So we know again that the sum of the forces is going to equal to mass times acceleration. Acceleration is equal to the sum of the forces divided by the mass, and the only force involved in this case is the force of friction. So it's going to be Fk divided by mass. Fk, we figured out, was 0.783. We need to use the entire number, so not this number here, but the entire number, and we're going to divide it by the mass, which is 0.17, and that equals to 4.61 meters per second squared backwards. So we need to have 2 sig digs in our answer, so our final answer becomes 6.1 meters per second squared backwards. Now D asks, calculate the puck's velocity as it leaves the rough ice and returns to the smooth ice. So that's going to be our VF. So I'd like you to pause the video and answer this question. So if we draw our diagram out real quick, we're going to see that the puck is going to be on this rough ice and then it's going to go to the smooth ice. During the rough ice section, it's going to have an acceleration of 4.61 meters per second squared that way. It has no force going to the right. We know the VI is going to be 19 meters per second that way as it enters. We are looking for VF, and we know the distance it travels is 5.1 meters along the rough ice. So what equation can we use? We can use VF squared equals VI squared plus 2AD. Okay, so let's plug our numbers in. VF squared is our question. VI squared is our 19 squared plus 2 times negative 4.61, because we said to the right was positive, times D, which is 5.1. VF squared is going to equal to 19 squared plus 2 times negative 4.61 times 5.1. So that gives a VF squared of 313.978. We can take the square root of both of these, and that gives us a VF equaling to 17.7 meters per second that way. We need 2 sig digs in our final answer, so our VF becomes 18 meters per second that way. And that concludes our lesson on friction.